Hello students! Welcome back to Chapter 2, Part 2. In this video, you're going to learn electromotive force and electrical energy. Do you know what electromotive force is? Electromotive force is the energy per unit charge converted from one form of energy into electrical energy to move the charge across the whole circuit. Electromotive force can be written as the equation shown below, where E is the electromotive force, W is the energy converted from non-electrical forms to electrical forms, and Q is the charge. The unit of EMF is joule per coulomb, or volt. Do you know why the unit of EMF is joules per coulomb? Based on the definition that we learned before, EMF is the energy needed to move the charge across the circuit. Joules per coulomb means 1 joule of electrical energy is supplied to the circuit to move 1 coulomb of charge across the circuit. Great! Joules per coulomb obeys the definition of EMF. Therefore, J over C can be used as the EMF unit. Instead of writing J over C, volt is much easier to be written. Given that 1 coulomb is equal to 6.24 times 10 to the 18 electrons, how many coulombs is equal to 1 electron? Please pause the video to try it yourself. Using the equality that was given before, we can divide both sides by 6.24 times 10 to the 18 to get 1 electron's worth of coulombs. Therefore, we get 1 electron is equal to 1.6 times 10 to the negative 19 coulomb. Now that we know that 1 electron is equal to 1.6 times 10 to the negative 19 coulombs, we can use the equation Q is equal to NE, where Q is the charge, N is the number of electrons, and E is equal to 1.6 times 10 to the negative 19 coulombs. Please note that a proton is equal to positive 1.6 times 10 to the negative 19 coulombs, and electrons are equal to negative 1.6 times 10 to the negative 19 coulombs. What is the difference between electromotive force and potential difference? Let's first look at the similarities between electromotive force and potential difference. The first similarity is that they use the same units, volts. The second similarity is that they're both measured by a voltmeter. Now let's look at the differences between electromotive force and potential difference. Definition of EMF states that EMF is the energy per unit charge that is converted from chemical, mechanical, or other forms of energy into electrical energy in a battery or dynamo. The definition of potential difference states that potential difference is the energy converted from electrical to other forms when 1 coulomb of charge passes between 2 points. The second difference between electromotive force and potential difference are their symbols. Electromotive force is denoted by the symbol E, whereas potential difference is denoted by the symbol V. To summarize, both electromotive force and potential difference have the same unit, volts, and can be measured by a voltmeter. Electromotive force is defined as the energy per unit charge and is denoted by the symbol E. Potential difference is the energy converted when 1 coulomb of positive charge passes between 2 points and is denoted by the symbol V. Let's look at the following circuit as an example. EMF equals 10 volts means that 10 joules of chemical energy is converted into electrical energy, and the energy supplied to the circuit to bring 1 coulomb of charge across the whole circuit. The potential difference of 2.5 volts means that work is done to convert 2.5 joules of electrical energy into heat energy to move 1 coulomb of charge across the resistor. 25% of the energy supplied by the cell is used to move the charge across this resistor. The potential difference of 7.5 volts means that the work is done to convert 7.5 joules of electrical energy into heat energy to move 1 coulomb of charge across the resistor. 75% of the energy supplied by the cell is used to move the charge across this resistor. Internal resistance, load resistance, and terminal potential difference. Inside the battery, we'll have internal resistance. Terminal potential difference is the potential difference across the two terminals, positive terminal and negative terminals. Every component inside the circuit will have load resistance. Let's look at this one example to make things more clear. If internal resistance is ignored, the terminal potential difference V is equal to the EMF E. Let's look at the next example. If the internal resistance is present, the terminal potential difference V will be lower than the EMF E. The relationship between EMF and the terminal potential difference is given by the following equation. E is equal to V plus IR. Since we know that V is equal to IR, we can say that E is equal to IR plus IR. The definitions for each term is given on the right side of the board. Example 1. A cell has internal resistance of 0.5 ohms, and a potential difference across the cell is 4 volts when 2 amps of current flows through it. Find the EMF of the cell. Please pause the video to try it yourself. To find the solution, we use the equation E is equal to V plus IR. Since we know that V is equal to 4, I is equal to 2, and R is equal to 0.5, we have that E is equal to 5 volts. Example 2. A cell with EMF 3 volts and internal resistance 1 ohm is connected to a 5 ohm resistance, and a voltmeter is connected across the resistor as shown on the diagram on the left. Find the reading of the voltmeter. Please pause the video to try it yourself. To find the solution, we can use the equation E is equal to I times R plus R and solve for I. Solving for I, we should get 0.5 amps. To find V, we use V is equal to IR. Solving for V, we should get 2.5 volts. There are 3 methods to measure EMF and the internal resistance. The first method is the open circuit closed circuit. The second method is the simultaneous equations. The third method is the linear graph. Let's look at the first method, open circuit closed circuit. In an open circuit, the switch is off. The voltmeter shows the reading of the EMF. In a closed circuit, the switch is on. The voltmeter shows the reading of the potential difference across 2 points. Let's look at an example that uses the open circuit closed circuit method. The diagram above shows a simple circuit that connects some batteries to the resistor. The voltmeter shows a reading of 5 volts when the switch is off and 4.5 volts when the switch is on. What is the EMF and the internal resistance of the cell? Please pause the video to try it yourself. When the switch is off, the reading of the voltmeter shows the EMF of the batteries. Therefore, the EMF is 5 volts. When the switch is turned on, the reading of the voltmeter shows the potential difference of the resistor. Therefore, V is equal to 4.5 volts. To find the current that passes through the resistor, we use the equation I is equal to V over R, which should give us 0.5 amps. Using the equation E is equal to V plus IR, we can solve for R, which gives us 1 ohm. Let's look at an example that uses the simultaneous equations method. When 1 ohm resistor is connected to a terminal of a cell, the current that flows through is 8 amps. When the resistor is replaced by a resistor with 4 ohms, the current becomes 2.67 amps. Find the internal resistance of the cell and the EMF of the cell. Please pause the video to try it yourself. Using the 1 ohm resistor, we have that E minus 8R is equal to 8. Using the 4 ohm resistor, we have that 3E minus 8R is equal to 32. Using these two equations, we have that E is equal to 12 volts and that R is equal to 0.5 ohms. Let's try to find the same things using a different example. The terminal potential difference of a battery is 1.2 volts when a 4 ohm resistor is connected to it. The terminal potential becomes 1.45 volts when the resistor is replaced by another resistor of resistance 29 ohms. Please pause the video to try it yourself. When V is equal to 1.2 and R is equal to 4, we have that I is equal to 0.3A. This gives us E minus 0.3R equals to 1.2. When V is equal to 1.45 and R is equal to 20, I is equal to 0.05 amps. This gives us E minus 0.05R is equal to 1.45. Using these two equations, we can solve that E is equal to 1.5 volts and R is equal to 1 ohm. Let's solve this example by using a linear graph. We know that V is equal to IR and that the gradient of a graph is equal to the y-axis over x-axis. Therefore, the gradient of the graph is V over I, which is the resistance R. The y-intercept of the graph is the EMF. The graph shows a variation of potential difference with current of a battery. What is the internal resistance and EMF of the battery? Please pause the video to try this yourself. We know that the EMF is equal to the y-intercept, which is 3 volts. We can get the internal resistance by dividing the EMF with the current, so R is equal to 3 over 6, which is 0.5 ohms. Now it's time to cover content 2 of the video, electrical energy. The formula for electrical energy is given by E is equal to QV, where E is the electrical energy, Q is the charge, and V is the potential difference. The unit of electrical energy is joule. Let's look at an example. Given that the potential difference across a bulb is 240 volts and the current that flows through the bulb is 0.25 amps, find the energy dissipated in the bulb in 30 seconds. Please pause the video to try this yourself. Using the equation E is equal to QV, knowing that Q is equal to IT, we can solve for E, which is equal to 1,800 joules. Do you know what electrical power is? Electric power is the rate of energy that is supplied to the circuit, which is joule per second. The unit for electrical power is watt. The formula for electrical power are P is equal to V squared over R, P is equal to E over T, P is equal to IV, or P is equal to I squared R. The meaning of each variable is listed on the right side of the board. Let's look at an example of power. An ideal battery with EMF 12 volts is connected in series to two bulbs with resistance 4 ohms and 2 ohms. What is the current in the circuit and the power dissipation in each bulb? Please pause the video to try it yourself. The potential difference across the two resistors is given by V is equal to 12 volts. The total resistance of the two resistors is given by R is equal to 4 plus 2, which is 6 ohms. The current in the circuit, I is equal to V over R, is given by 12 over 6, which is 2 amps. Using the equation P is equal to I squared R, we can find that the power dissipated in the 4 ohm light bulb is P is equal to 2 squared times 4, which is 16 watts. The power dissipated in the 2-ohm light bulb is P is equal to 2 squared times 2, which is 8 watts. In conclusion, in series connection, the greater the resistance, the greater the power dissipated. Let's look at the next example of power. An 800-watt heater is used to heat 250 cm³ of water from 30 to 100 degrees Celsius. What is the minimum time in which this can be done? Please pause the video to try this yourself. To find the energy supplied by the water, we can use the equation E is equal to PT. To find the heat energy absorbed by the water, we can use the equation E is equal to mc theta. Let's assume that all the energy supplied by the heater is converted to heat energy and absorbed by the water. Hence, PT is equal to mc theta. Solving for t, we should get 92 seconds. Power rating. This is an example of a power rating label. 240 volts and 1200 watts means that the electric appliance will consume 1200 joules of energy per second if the potential difference across it is 240 volts. Cost of electricity. Kilowatt hour, or kWh, is the energy used by a device at a rate of 1000 watts in an hour. 1 kilowatt is equal to 1000 watts times 60 times 60 seconds, which is 3.6 megajoules. Let's look at an example of electricity cost. If TNB charges 22 cents for each kilowatt of electricity, calculate the total cost of using 2 kilowatt electric kettle for 15 minutes and a 20-watt bulb for 8 hours. Please pause the video to try this yourself. Using the equation E is equal to PT, we can find the electrical energy of the kettle is equal to 0.5 kilowatt hour. The electrical energy of the bulb is equal to 0.16 kilowatt hour. The total electrical energy is therefore equal to 0.66 kilowatt hour. We can therefore find that the total cost is equal to 14.52 cents. The efficiency of electrical appliances. Efficiency is equal to power output over power input times 100%. Efficiency is always less than 100% due to the energy loss, such as heat and friction. Let's look at an example of efficiency. An electric motor raises a mass of 2 kg to a height of 5 meters in 10 seconds. If the input current from a source of 12 volts is 2 amps, find the efficiency of the electric motor. Please pause the video to try this yourself. To find the solution, we first need to find the input power. Using the equation P is equal to IV, we find that P is equal to 24 watts. From here, we can find the output power as P is equal to W over T, which gives us P is equal to 10 watts. Efficiency is therefore 10 over 24 times 100%, which is 41.7%. So what are some steps you can do to save energy? You can buy high-efficiency electric appliances. You can also use appliances with automatic power off functions. Congratulations! This concludes our lesson for Chapter 2. I hope to see you all back for Chapter 3. Bye!